to get started. And so, first of all, I would like to introduce the jurors in this fight. On my left-hand side is Professor Zhuang Zhenhao, and Professor Lin Zifeng, and Professor Lan Yanwen, and Professor Xu Hongwei. Right, and I am Chen Chuanren from Taiwan National University. And now I would like you to introduce yourself. We'll probably start from the reporter.
I'm Justin from Typt American School, and this is Alex, this is Charlene, this is Yunho, and this is Green.
And reviewer.
Hello everyone, we're Ningdao Ling. I'm from Ningdao High School. This is Sweeney Lin, Jerry Cow, Ray Cool, and Robert Lin, and this is Sarah Wu.
We're Team Ipsen from Kaohsiung Senior High School, and I'm Xu Yisheng, Chou Yude, Xie Haoren, Wang Lingshen, and Li Haozhe.
All right. So now the opponent has 1 minute to challenge the reporter.
We would like to challenge problem number 2, oscillating the field.
And number 2. And reporter, you have 1 minute. Consider.
We accept.
Okay. Problem 2 is a section. All right. And now our reporter has 5 minutes to prepare. And at the same time, please write the representative on the breadboard. time for reporter report.
Hello, today I'm presenting oscillating sphere from all-nighters from Charlie. So the problem statement states that as a light sphere with a conducting surface is suspended from a thin wire, when the sphere is rotated about its vertical axis, thereby twisting the wire, and then released, it starts to oscillate. Investigate how the presence of a magnetic field affects the motion. So the focuses would be on magnetic damping, magnetic uniformity, and the surface of the sphere. So for phenomenal observation, what happens is that when a metallic sphere is placed into a magnetic field, this generates an induced electric field, and this causes eddy currents to form. And the currents experience a force which generates the de-spinning torque. So defining the coordinate axis on the setup, so y is into the board, z is along the magnetic field, and x is up and down. So as for the movement of the sphere in B, this is the orientation where the applied B field is into the board. And so the velocity of the ball is along the orange arrows. And so using the right-hand rule, you get that the current loops up and then down the other side. And so using the right-hand rule again, you get the opposing force going this way. And using the other orientation where the applied B field is out, the velocity is also around the orange arrows, and that creates a current looping from the back downwards. And overall, this is the top downwards. So the orientation of the magnetic field. When the B field is parallel to the rotational axis, there's no torque or damping. And when the B field is perpendicular to the rotational axis, there is torque or damping. So damping. When the B field is perpendicular to the axis of rotation, there's observed underdamping. So what it is that it slows the back and forth motion but allows for oscillations. So this is described by the following equation. So experimental setup 1. The main setup of our experiment involves using this. And so our experimental setup 2 is when the B field is perpendicular to the rotational axis. And so the two solenoids are arranged in the form of a Helmholtz coil. So in a uniform magnetic field, it is exerted parallel to the rotational axis. So when the two solenoids are arranged in the form of a Helmholtz coil, it is the same setup except turned over. So in a uniform magnetic field, it is exerted perpendicular to the rotational axis. So for the data collection, so regardless, what we do is we track the motion of the sphere using tracker, and so we put it into Python, and what that yields is a fit graph as such. expression method, what we did was we pushed a magnetic field sensor through the magnetic field. And so what we got was, we used the peak value obtained from this graph to measure the magnetic field at the center of the ball. And so an analysis method was used by tracking the sphere. And so we inputted the data into Python and fit it to the underdamped fit. And so here's a Python generated fit. This is the example fit graph. It fits extremely well. And so as for the difference between uniform and non-uniform magnetic fields, there should be little difference between the effects of uniform and non-uniform magnetic fields on damping. So the error is due to the non-uniformity in the field, but it is minimized by torque. So torque decreases away from the center of the ball. So the edges are also where the non-uniformity is based, so that's why it doesn't matter. So we also use coupled magnets, and the center is most coherent in terms of magnetic field, and the difference should be an error. So the gradient of the magnetic field shouldn't affect damping, as it is already a sort of built-in gradient, as the shape is 3D and spherical, where the current goes up one side and down the other. So here we do an experiment for uniform magnetic field versus non-uniform magnetic field. So as you can see from the slopes over here, the slopes are approximately the same. So this shows that graphing b squared over gamma, which is a damping constant, the relationship is pretty much the same, and therefore the torque opposing the motion of the sphere is approximately the same. So theoretical model, we're assuming that the conducting surface of the sphere is entirely smooth. There's only torsional motion and no pendulum-like motion, and the glue attaching the wire to the sphere is negligible. So damping contribution. So our preliminary theoretical model for additional damping due to the magnetic field is depicted by the standard damped harmonic oscillator equation as such. So EMF should equal around omega br squared, I equals this, and then torque equals RF, and that should yield that equation. And so as a result, our damped harmonic oscillator equation for this particular phenomenon should be depicted as such. However, it should be noted that this is an oversimplification of the problem, as it does not account for the velocity at each point of the sphere. So moving on, we do a more rigorous theoretical model. So this is taking into account everything, almost everything. So V equals omega cross R, that induces the electric field, which is V cross B, and that is the position vector combination. These are supposing they're cylindrical magnets. J over here is the current per unit volume, and that yields this expression over here. So this is the force per unit volume using J cross B, and then we get the torque per unit volume, which is R cross F. And using shell volume integration over the entirety of the surface of the shell, of the sphere, we get that the total torque acting on the sphere would be that. So thus the constant alpha is 2 pi over 15 for a solid sphere. So our governing equation for experiments would be depicted as such, where gamma is a damping factor, whereas the gamma naught is a damping already present without the magnetic field. So our theoretical proportionalities we would want to verify would be these over here. Experimentation and discussion. So our magnetic field orientation, when it's parallel to the B field, is that at 0 milliteslas, gamma, and at 6.2 milliteslas, the gammas are around the same. So that just verifies that it indicates magnetic damping when there is no magnetic damping when the magnetic field is oriented parallel to the rotational axis. So experimental, for varying material, we see a linear relation which matches the theoretical expectation. What we're doing is that we are graphing B squared over I versus gamma. And so what we see that is that aluminum has the highest slope, brass has the second highest, and tin has the lowest. And however, based on the resistivity values, aluminum has the lowest resistivity values, and that this thus indicates an inverse proportionality between the damping constant and the resistivity of the material. And moving on, the experimental, another experiment we did was varying the radius of the ball. So what we noticed was that as we increased the radius of the ball, the slope increased. So that matches theoretical expectation. What we did was we also did an experiment with the ferromagnet in a B field. So as you know, the steel ball, as the steel is a ferromagnet, so when put into a B field, it would have essentially a steel ball has the characteristics of a ferromagnet. So as you can see, based on the slope values, the steel ball's slope value is in between that of the brass and the tin. And so since the steel ball's resistivity is higher than that of the brass and lower than that of tin, it follows the general trend that we talked about. However, it should be noted that the steel ball is a ferromagnet, and so there's a possibility of hysteresis. So as we go through the different trials, there could be permanent magnetic dipoles induced, which would also affect our experiment. So we cannot reasonably design an experiment for that. And we also need to take into account that the ferromagnet's interaction between with the magnets would also induce it would also create this additional magnetic force, which would lead to damping. So conclusion. So as the motion in the magnetic field creates current, it induces an electric field, creates the current, and the current experiences a force. So our experimental data is modeled by the linear equation as such, and the magnetic field is parallel to the ball, resulting in no damping, and the perpendicular results in damping. So increasing surface resistance and the radius of the ball increases damping. So damping increases with the strength in the magnetic field and the radius of the ball. And so we verified the theoretical proportionalities over here. Thank you.
So it's time for opponent to expression.
Thank you to the reporters for your presentation. Could you move on page 6? Could you please tell me the radius of your spheres and the radius of the dipole for the two electromagnets? Because it seems that the sphere is larger than the dipoles. Am I correct?
Sorry, you mean that it's larger than the surface of the
Yes. Could you
magnet?
tell me the diameters of the spheres and the diameters of your dipoles between the two magnets?
So the sphere has a diameter of 2.54 centimeters.
And about the dipoles, about your electric magnets?
Sorry, your
The diameters of your electromagnets.
diameter of,
Yes, the area.
well, it should be around the same, because when I put it in,
The same?
it was the same.
Okay. And please turn to page 7. That will show the direction of the eddy current. So you think the eddy current is parallel to your magnetic field direction?
Correct.
Okay. Okay. And please turn to page 9. In your damping equations, did you complete back to your exponentials? Is there any? Do you think there should be a time product after your gamma? Since I don't remember about the equation about the underdamping, could you tell me there should be a time after your exponential product? Okay, please. Or please change to page 14. What are your
And now the preparation for the opponent in 2 minutes prepare. 3 minutes.
fellow competitors, I'm the opponent from Team Typt. For the problem state, problem number 2, oscillating sphere, we think the main focus should be the conducting surface that works in a magnetic field. So the presence of the magnetic fields affect the motions will be the main focus about this question. And about the summary, for the theory, they mentioned that the magnetic field will also provide an eddy current on the sphere that makes the ball resist. So they calculated the damping terms about the magnetic damping and plus the damping that the sphere provides, and to calculate the underdamping coefficients. And the motivations EMF will also consider in their theory. And for the experimental setup, they use a conducting surface and a coil, but I can't agree with the reporter that the coil is uniform, since that the diameters of the coil is equal to the diameters of the conducting sphere. And about the parameters, they use a different strength of the magnetic field and different materials for the conducting sphere. And about the method, they use Python to analyze the experimental result and use tracker to track the point on the sphere to calculate the angular velocity. And about the magnetic, they use the magnetic field sensor to measure the magnetic field on the sphere. And for the conclusion, the magnetic fields will create the currents on the ball and lead to damping. But the direction of the currents that are provided on the balls, I would like to discuss further and increase the surface resistance and the radius, and damping increase while the magnetic fields increase. And about the strength, about the reporter's report, I think they have a completely quantitative phenomenon explanation about the eddy current lead to the damping. And a lot of experiments to prove their assumption in their theory, which is the damping will proportional to the alpha. And the assumption have been also provided a lot in their experimental result, their theory model. And they have good experimental setup, which they use the electromagnet to control the magnetic field. And about some of the area for improvement, they have lack of quantitative comparisons between the theory explanation. In the graph, they didn't show that they calculated the only part about the magnetic damping, and lack of explanation for the experimental result. They show because about the unclear y-axis that I would like to discuss about, and the analyze method didn't also be mentioned, and an unclear physics picture, and which is a simple explanation about the phenomenon in the theoretical model. The derivation about the direction of the eddy current didn't been explained well. And for the assumption, the resistance didn't clear. And the uniform coil, which is the most important question I would like to ask, is since the diameters they mentioned is equal to the coils, I think the uniform magnetic field doesn't act on the experimental setup, and they have unclear graphic explanation. And then I would like to show the underdamping equation here. And for the textile film, I will think the reporter has the partly fulfilled about this problem. And I would like to start my discussion now. Okay. Could you turn to page 6? Let's start off the uniform magnetic field we are talking about. So about the diameters of the sphere and the diameter of the electromagnet, I think this is important to provide a uniform magnetic field. So in your theoretical model, did you calculate it on uniform magnetic field or uniform magnetic field?
So I think you misunderstood while I was reading. So for this slide, what this was that it was a non-uniform magnetic field. The uniform magnetic field was for the next setup, which was the solenoids. If you recall that I had 2 solenoids, and in that case, the diameter of the solenoid was bigger than that of the sphere. I think that's what you got.
So your magnetic sensors also only measure the magnetic field in the 3 axes. So did you assume that every single positions on the spheres, the magnetic field is equal, or the current density is equal?
You mean as for this setup?
Yes. So could you tell me the diameters of the electromagnet?
This is not an electromagnet. This is these are coils.
Okay, then the diameters of the coil.
It should be 60.
And about the sphere?
1 inch.
And so that, do you think the uniform magnetic field is important in your theory to compare the theoretical model and your experimental results?
So could you repeat this?
The uniform magnetic field is important?
No, it is relatively unimportant. So the reason why I used most of my experiments using the other setup with the electromagnets was because using magnets can generate a larger magnetic field, and so that can give our data a large range.
In my opinion, I think the reasons that I think the uniform magnetic field is important because in the duration about the reported theoretical model, I think they just consider about the uniform magnetic field. So if the diameters of the electromagnet is smaller or equal to the of the spheres, I think the uniform magnetic field should be considered in the theoretical model. And about another question is about problem number page number 7. Page number 7. I would like to discuss about the current direction of the sphere. Could we move on the blackboard? So you have mentioned that the densities current is equally in the spheres. Current densities.
Current density is not equal.
Okay, so direction will parallel to your magnetic field. Is that correct?
Correct.
So, since that the sphere is hard to be discussed, I would like to take a part of the spheres for discuss. Is that okay?
Okay.
So, when we discuss about a ring, that we take a small part of the sphere as a ring. Is that okay?
So you're modeling it as a wire.
That we take a part of the spheres for discuss about the direction. Is that okay?
Right, sure.
Okay, so do you know that according to Faraday's law, the induced current will relate to the flux of the magnetic field.
Right.
So under this circumstance, do you think when your ring is parallel to your magnetic field, is there any magnetic flux under this circumstance?
No.
So why do you think the direction will parallel to the about your magnetic field?
Sorry.
So can you explain
Okay,
why
so
do you
what
think?
I was talking about in regards to parallel magnetic fields to the rotational axis
Yes.
was that when the B field, for example, is like this, there's no force.
There's no torque. So
I think you misunderstood
no,
what I
okay. I'm talking about the cases under your magnetic field is vertical to the rotation axis. You mentioned that it will cut the eddy current.
Correct.
And the direction of the eddy current will be the same with the magnetic field. Is that correct? Will parallel. So the reason I would like to discuss it because since the direction of your eddy current is parallel to the magnetic field, I don't think there's any magnetic flux. So I think the direction of the eddy current should be clear again.
Okay,
So I suggest the reporter can explain this again.
Yes, I would like to clarify what I meant.
Okay.
So actually what I meant was that when you exert, for example, a B field into the field, right? So, and then it's rotating like this. So the velocity is going like this.
Yes.
So using the right-hand rule into the board, B field into the board, so this would be the B field into the board. Velocity is in this direction. This generates force B upwards. So that would create a current like this, right? So that would create a looping like this, essentially.
So
Since it is 3D and spherical, it would go like this.
So you think it's vertical? The current is vertical to your spheres. It's vertical to your spheres.
I'm not quite sure what you're saying.
In your graph here, you show that the current is parallel to the magnetic field, which I will drawing like this. Is that correct?
No, okay, so that graph over here, it's generated using like PowerPoint, right? So I just want to make it more visual.
Yes.
So this is essentially the same thing as that.
And so in my opinion, I think the reporter has wrong directions about the currents that they provide in the graph. since that we all know that the induced current can relate to the epsilon here.
Right. So I agree that it is like the flux thing applied. Right?
Yes.
But then in this case, like when the sphere is rotating, it's always in the presence of a magnetic field.
Yes.
So essentially, when this is these are magnets, right? So north to south, this goes like this. The sphere is always within the magnetic field. So I think it is irrelevant as to considering the EMF.
So I agree to report that will be the current density, current on the spheres, but I think the direction is wrong. So the next question I want to ask is page number 9.
It was a typo.
Okay. And about the problem, page 14. Sorry, page 15. About that you show your experimental graph. May I ask about your y-axis? Seems that it's a theta. Is that correct?
No, it is. Well, it is a position of the sphere when it's oscillating.
Okay, so but in your damping terms, you mentioned that the damping was proportional to the accelerations. Is that correct?
Damping is proportional to
The acceleration.
acceleration is proportional to omega angular velocity.
So acceleration, angular velocity, alpha.
Well, just like the fact that torque was I alpha.
Yes. So the torque is I alpha, but the graph here you only show the positions of the theta.
Oh, sorry. So to clarify, this is a Python generated fit. This was
Okay, so
in order to get the
please
damping
turn the
constant.
page that you show the experimental result.
Which experimental result?
So could you tell me the y-axis? Since that you only mentioned about the magnetic damping.
Right. So damping constant is this value, and this is B squared.
So another question that I want to ask is the equation that you provide for the magnetic damping. Let's you move on. So you think the damping terms were proportional to the conducting coefficients? Is that equation
That is
correct? In your conclusion, I believe. Right? So you think when the conducting coefficient is decreased, the damping will increase.
Right.
So that we know. So if you use a thing that is very the coefficient of the conducting is very small, that the damping will be quite big in your situations. Is that correct?
Well, so essentially what I mean by resistance is that, well, I guess you could sort of, just like, in a simplified way, you could sort of model it as,
Okay, so in my opinion,
wire.
I think the relationship between the dampings and the conducting coefficient should be wrong. Since that if we use a very small conducting coefficient object that's rotating in the magnetic field, maybe the current densities will be very small. So I think the reporter should be more clearly about the durations about the current densities. And thank you for the reporters answering my question.
Thank you for a great discussion.
Apollo, you want to summarize?
Thanks for answering about the reporter. First, we discussed about the experimental setup. Since I think that uniform magnetic field is very important in their situation, since the diameters they say is equally to the diameter of the sphere. So I think the uniform magnetic field will be provided. Another that we discussed about the direction of the current that they provide, and I think the reporter. I agree to the reporter that the AD current will be provided in the spheres, but I don't think the direction will be parallel to the magnetic field since there's no magnetic flux in their circumstance. And about the damping, that I think the relationship that they provided with the conducting coefficient will be wrong, since that if we provided a thin object that have a very small conducting coefficient in the magnetic field, the AD current shouldn't be so big. So another question that we discussed about is the damping equations. That in the damping equation is not time dependent. I think that it should be suggested.
So it's a question time for the reviewer to raise a question, both the reporter and opponent.
Okay, so the first question for the reporter and the opponent. What do you think, respectively, the most important factor about the damping in this experiment? The most important for the damping? The magnetic field.
I think the magnetic field that they provided.
Okay. Can you re-explain about the damping constant? I don't think I got it very clearly. The damping constant. So the damping constant just is an indication of how much damping there is. Like you can get torque based on it. Okay, and as the opponent asks about the exponential time for your formula that you mentioned about, do you think you should do the correction? So he has mentioned about the in one of your damping formula, you probably miss a t, the time factor. Do you agree that? It was a typo. It was a typo. Oh, I apologize. And what do you think hysteresis is negligible? I don't think it's negligible. I just think it cannot be accounted for. It cannot be accounted for. But if someone were to provide a way to prove that would be beneficial. Okay. Do you think there are other parameters that should miss in this experiment?
I think the thickness about the sphere will also should be considered, and I think different incline angle about the sphere. I think can also be considered, since that about the magnetic flux. I think the reporter has some misunderstanding about the direction of the AC current.
Do you agree what he said about the thickness of the sphere? Yeah. I definitely agree that the thickness of the sphere will affect. So I use solid spheres in this case, and the current will go down to a certain safe depth. And so why do you think when we're talking about direction, you guys probably have something that's misunderstanding? Why do you think caused that?
Since I think the reporter says that AC current will parallel to the magnetic field, but in my opinion, I think if the AC current will parallel to the magnetic field, there is no flux will be applied. Magnetic flux will apply in this circumstance.
Okay, I will finish my question.
Preparation time for reviewer, 2 minutes.
everyone, I'm the reviewer from Delmia, and the topic I'm going to talk about is problem number 2, the oscillating sphere. So we think that the main focus of the discussion should be on the magnetic damping, the magnetic field, and the conducting surface, the both have mentioned above. Overview for the reporter. Their advantage include the fair explanation of the phenomena, have a clear graph for showing how each direction of oscillating affects the current, and also talk about various factors influence the damping. For example, the material and the radius of the ball, and the ferromagnetics. And also the suggestion for the reporter, she should have demonstration video as well. And the second, she didn't explain the parameter in each formula in detail. For example, the damping equation the opponent has mentioned about. And it shows a bit show clearly about the theory and its derivation. Is going too quick a little. And the overview for the opponent of his advantage include that he found out detailed mistakes of the reporter, for example, the setup portfolio. And the second, he also asked the thoughtful questions. And the third one, he provided answers to their own questions as well. And the suggestion for the opponent, he could probably have give the reporter more time for demonstration and explanation. And about the first discussion, let's start with the uniform magnetic field. And the opponent said that it's not uniform. And the opponent said that he asked about the diameter of the coil. The reporter answered 6 centimeters. And they talk about the impedance, but the reporter said that no, it's not important, just for better observation. But the opponent thinks that for a formula, the opponent thinks that the reporter only considered the uniform, and the reviewer agreed with the opponent. And for the second discussion, they talk about the position of the magnetic field, and the reporter gives demonstration of the AD and the velocity direction. And the opponent mentioned that she should try to clarify on the AD direction. But the reviewer thinks that they probably have some misunderstanding about each other's direction that they're referring to. So this is why caused the calculation difference. And the opponent thinks that the direction is still wrong due to a formula we use. And for the last discussion, the opponent asks about the chart and the equation for damping. And the reporter says that she used a simulation, so she probably didn't take that into account. And opponent continued with the conducting coefficient. When the conducting coefficient is low, as the formula he has wrote on the blackboard, the damping will be high. And finally is our conclusion. The reviewer thinks that the uniform coil or not is very important due to the observing results the reporter gives and the opponent talks about. And also the thickness of the sphere also affects the probabliness in the reporter's presentation. And finally, since the two have misunderstanding about the direction, so it's probably better to clarify that initially so they can have a better discussion. And this is much of my reviewing section. Thank you for listening.
So it's time for the reporter to conclude.
Okay, so thank you for a great discussion with the opponent. So the report confirmed the uniformity of the magnetic field for the coil, and the motion in the magnetic field creates a current. It induces an electric field which creates current, and the current experiences a force. So our experimental data is modeled by the linear equation gamma equals gamma naught plus over here. And so we verify the theoretical proportionalities of gamma proportional to p squared over I, gamma is proportional to radius, and gamma is inversely proportional to resistance. And so eddy current is 3D, so what I think we got confused, like the reporter and the opponent had disagreeing viewpoints is because I think the eddy current is 3D, so the current goes up one side and the other, so it's a circle, so there's a different direction of the current at each point. So it's not necessarily parallel as what the opponent assumed. And so we get the direction of the current using right-hand rule to clarify. And so we didn't use a simulation for my experiments. It was just for fit using the underdamping equation to get a damping constant for the review. And so changing the thickness of the sphere, like how, if you were to use it by changing the thickness of the sphere by perhaps using aluminum foil, you would have to account for the uneven surface, but that would that would include many other variables that we can't necessarily account for, such as the uneven surface and stuff like that. So thank you for a great discussion.
All right, so it's time for jury to ask questions. Any questions from viewers?
Okay, so I would like to ask on three of them. So maybe you first.
Okay.
Okay. So what happens if you consider the non-uniform magnetic field?
I think the non-uniform magnetic field will make the current densities in different positions of the ball will be different. Is that correct?
Well, I think the most important part of that influences like the damping due to the magnetic field is the center of the sphere, because torque decreases away from the center of the sphere field. And the non-uniformity is mostly on the edges of the sphere, so since we only really take into account the area and the center of the sphere, we don't really take into account the edges because the torque is not, the torque decreases as it goes down.
I think for the non-uniform coil, like the distance is already different, so it will definitely affect the magnetic field about the density of the magnetic field. Yes.
Just one small question for the reporter. Because you rotate your ball, right? So how can you control the rotation velocity?
So the initial angle that we displaced it.
Yeah, so how can you control or make sure it's the same velocity? Rotation velocity? How can you control the same velocity?
So I account for the initial angle in my Python simulation, not simulation, by the Python fit by adding a constant e to fit it to, so it would account for the non-constant initial conditions in terms of twisting the sphere, because it's quite impossible to twist the sphere at like this exact angle, right? Because there's always human error. So we account for that in the Python.
Okay. So it means that you will rotate by yourself. There will be a little difference in the initial velocity.
Right. So I try to account for it in the.
I have a question for the component. Is that easy for you to find a different thickness of the sphere? I mean the thickness.
I think that the reason that why I think the thickness will affect the result, it seems that the conductive materials in our real life is not ideal conductive material, which means there's also they will provide an electric field inside the materials.
Yeah, my question is easy to find a different thickness of the sphere. Is that for you easy to find?
To create an experimental setup, maybe it is hard, but about the durations, they should consider the thickness of the whole of the spheres is to be considered.
Excuse me, I think I would like to clarify the question you asked. Is that possible? Thank you. As for like the non-uniformities effect, so the whole point of using a non-uniform magnetic field for us was to generate a large range of magnetic fields so that our data could be more wide range. And so I definitely feel like it would affect, but I think it would affect by a small amount because the torque decreases away from the center.
Okay, so I have one question since the question to you guys already been asked, so now for you, so only to the reporter. I just want to make sure I did not miss something. So do you have do you really measure the damping constant, the gamma?
I found it using the fit.
But in your data, do you determine, do you finally determine the gamma from the data?
So gamma is a constant that can be obtained when we fit the data to the underdamped.
Right. But this plot is for the real data or the
Yeah, it's
just
real.
This is the real data?
Yeah.
It's a Python generator.
Python generated.
But
It's not real
But it's
data.
not real data, it's, I mean, from your observation, from your data, you take it. It's not from the Python.
You have the real number for the gamma
For your
from
data,
experiments.
do you mean,
The point, the red point on your screen is the real data, right?
Yeah.
But the white is the Python speaking.
Correct.
Yeah, okay.
Yeah, so the
The data, real data is
is,
point data.
the data is right. And then so
Okay.
the blue line is like the,
Python.
the underdamped.
So they use the Python.
Both to
I
put
use
it on the
Python
one
to
graph.
fit it
Yeah,
there, so I can get the gamma.
Maybe next time you can mention the point is the real data.
Oh,
But the
okay.
fitting data is the blue white.
Oh, blue line.
Okay, all right.
Yeah.
Oh, sorry for the.
Yeah. We are thinking about the probably in the other ways, using the theory calculation to figure out the
Python.
Yeah.
Yeah, so probably. Ready?
Yes.
Okay, so the point for reporting. It's 7, 8, 8, 7, and 7. And about the opponent,
Maybe you didn't put the right number, not right score. Oh, okay, so it doesn't matter then. huh?
Yeah, it doesn't really matter, they have it. So the point for the opponent is 8, 8, 8, 7, and 7. And finally, for the reviewer, seven, eight, eight, 7, and 6. Okay, so that's it for this fight. Then we have super 15-minute break. All right, so please have a seat. All right, so now opponent has 1 minute to challenge the problem.
We want to challenge question number 4, color line.
Problem number 4. And reporter has 1 minute to consider.
We accept the challenge.
Okay, number of points accepted. The reporter has 5 minutes to prepare. as a reminder, you can take off your best man if you like when you speak. Reporters.
Honorable judges and fellow competitors, I'm the reporter from Team XL, and today's topic is problem number 4, colored line. And for a problem statement, when the contact distorted DVD is illuminated with light coming from the filament bank, in such a way, the only rays with large angles of incidence are select. A clear green light can be observed, and the color varies from slightly changing the angle of the disc. And I'm going to explain and investigate this phenomenon. According to the problem statement, my main focus of this problem is investigate results by changing the angle of incidence and investigate results by changing the CD to the DVD. And here's the context of my report. For the observations, first, we can see when the light source sends the light rays to the disk, a clear line can be observed. And we also notice when we change the place of the light source, the position of the line will be different. And for here, we can see when the city is illuminated, a clear green line can be observed. And when we gradually incline the disk, the color of the line on the disk will be different. And here's my theory. First, I'm going to talk about the structure of the disk. For the figure on the right, we can see that the city's bottom surface spiral patterns of alternating pits and lengths, and thousands of pits are arranged in the form of spiral tracks. And when the light incidents at each tracks, the tracks will reflect the light back, which means when the city is illuminated light, it can access a diffusion grating. And the diffusion grating is an optical component with periodic structure that differs light into several beams traveling in different directions. The diffraction angles of this beam depend on the wave incidence angle, the distance between adjacent diffracting elements, and the wavelength of the incidence light. And for here, I'm going to explain about why when the light source sends the light rays to the disk, the clear line can be observed. And for the figure on the right, we can see both the observer and the source of light are placed at the same horizontal plane. And the light source will send the light ray at any frequency in the visible spectrum. And when the light rays is incident on the diameter that bisecting the OAs through a point P and P prime, for example, the light rays will reflect back to the observer, and the clear line can be observed. If the light is incident at point P prime, which is not on the bisecting diameter that go through a point P and P prime, the light will reflect in the direction away from the observer. And for here, I'm going to talk about the differences between the CD and the regular diffusion grating. First, on the figure on the left, you can see there are spiral tracks on the CD. And when the light is incident on the diameter of the CD, you can see the tracks on it is a periodic structure, which means when the light is incident on it, the reflected light will undergo interference, and the clear light can be seen. But if the light is not incident on the diameter of the CD, you can see that tracks on it is not a periodic structure, which means there is no interference, and no light can be seen. And for the regular diffusion grating, we can see all the slits on these are parallel, which means no matter where the lights are incident, the reflected light will undergo interference. So when the diffusion grating is illuminated, it will shine. And for the picture here, on the left, we can see when the light is not incident on the diameter of the disk, there's no line on it. If the light is incident on the diameter, the clear line can be observed on the disk. And here on the video on the left, we can see that when we change the place of the light source, the position of the line will be different. And for the figure on the right, we can see when we place the source of light at point S, the diameter that bisecting the OAs will go through the point P and P prime. But if we change the place of the light source to the point S prime, we can see that the diameter that bisecting the OAs changing to the point R will go through a point R and a prime, which means the position of the line will be different. And for here is my formula derivation. And for the reference below and by the picture on the right, we'll have the equation 1 as the slideshow. And by the approximation of the scalar diffusion theory, the observer at O will see the light rays at the frequency mu equal to C over lambda equal to K over 2 pi from each track characterized by the following expression of the electric field. And only the real part of EM is considered, and by summing M equal to 0 to N, the total electric field at any frequency delivered from P to O can be as equation 3 below. And when we set the K tilde equal to the K over cosine alpha, we can have the equation 4. And according to the Euler's formula, we can write the equation as below. And since we know that the light intensity I at O is proportional to the E squared, we'll get the equation 6. And by recalling that the K tilde equal to K over cosine alpha equal to 2 pi over lambda cosine alpha, finally we'll get equation 7 here. And for the figure A on the left, we set the maximum of this curve value of the quantity A over lambda cosine alpha equal to an integer n, so we'll have the equation A as here. And for using the picture on the right, and by the same analysis, we can change the equation A into the equation B. And when we take the situation of A close to 0 degrees and beta equal to 10 degrees, for instance, the A over cosine alpha can be taken to be 1.6 micrometers. And according to the equation B, for m equal to 1 to 4, we can get the different lambdas below. And we notice that only the lambda 3 and lambda 4 are visible. but the intensity of the green light is bigger than the blue light, and the human's eye is more sensitive to the green light. We will only see the green light on the CD. And here's my simulation of the theory. The tools I use is the Python and the Jupyter Lab. And here's the result of the CD. So we can see when we have the different end of the for different order, we can see when we change the angle alpha or angle beta, the color that shows on the CD will be different. And we combine this all situation together, we can get a figure that shows the intensity of the light. Or here, we can say when we set the same angle alpha and change the angle beta, we can see that the color of the line will be different. And we can have the same simulation for the DVD. And when we combine the situation together, we'll still can get a figure of the intensity of the light. But we can see that when we change the beta degrees, the color that has the maximum intensity will be different from the CD. And here's my experiment. For my experiment setup, the location we need is darkroom with no mirrors, since the mirror may have some reflection that affecting our experiment. And the device we need is a disk. The protractor is to analyze the angles between the source of light and the disk. And the lighting equipment, and here I use is the filament lab. And for my first experiment, the parameter I use is the incidence angle theta. And the theta is angle equal to the 90 degrees minus angle beta. And for measuring, I'm going to use the efficient to analyze the wavelength of the line. In my control variables, the type of the disk is the CD. And the equation that I'm going to use to analyze the wavelength of the color line is the equation B here. And by using this equation, we can have the wavelength of the reflect light, and which is the wavelength of the color line. And here's the video of my first experiment. And here's my result analysis of my experiment. The chart on the left is my result of the experiment. And the figure on the right is my simulation of the theory. So when we set the angles of incidence is 80 degrees, which means the angle beta is 10 degrees, we can see the color on the disk is green. And when we change the angle into 75 degrees, we can see the color on it is not various. It still be green. And we have the same result when we change the angle into 70 degrees. But if we decrease the angle into 65 degrees, we can see that the color of the line varies into red. And we can have the same result when we change the angle into 60 and 55 degrees. And here's my second experiment. The parameter is still the incidence angle theta. I'm going to use the equation to analyze the wavelength of the line. But for my control variables, the type of CD here I use is the DVD. And here's also my video of my experiment. We can see that the color will vary when we change the angle of the disk. And here's the result analysis of my second experiment. First, we can see when the angles of incidence is 80 degrees. The clear violet line on the disk can be observed. And we have the same result when we change the angle into 75 degrees. And we can see the color of the line will vary into red when we change the angle into 70 degrees. In 65 degrees, we can see that the line on the disk is still red. But when we decrease the angle into 60 degrees, we can see that the color of the line on the disk change into orange. And when we change the angle into 55 degrees, we can see the color varies into green. And here's my conclusion. First, we can see that the angle between the normal and the source and the disk influence the wavelength of the reflect light, and which is related to the color of the line. So for the figure here, we can see when we gradually entire the disk, we can see both the color of the line on the CD and the DVD will change. For CD, the color will from green change into red. And for DVD, the color of the line will from violet change into red and finally into green. And for here, we also notice that the distance between adjacent splits will also influence the color of the line. So for the figure on the left, we can see that the spacing of the CD is 1.6 micrometers. And for the DVD is 0.74 micrometers. We can see the spacing of the CD is smaller than the CD. So when we change the CD to the DVD, when we have the same angle beta and the same angle alpha, we can see that the color of the line on the CD and DVD are different. For CD, it's green line, and for the DVD, it's violet. And here's the end of my presentation. Thanks for your attention.
Right, it's time for opponent to raise a question.
Hello, my first question is that you do know that there are different levels of diffraction, right?
Yes.
Okay. And then, so how did you actually change the angle? Was it like you changed how do you define your angles of incidence? Is it like the angle this way or the angle this way?
For my experiment, the angle of incidence means that the distance, the angles between the normal of the disk and the light source. So the angle theta is like the angles between when the light source sends the light rays to here and the normal of the disk is here. The angle theta, which means the angle of the incidence, is this part.
This look right?
Yes.
Okay, thank you. And did you know that there are actually more than one layer in this?
Yes.
And do you think that it matters?
For the layers of the disk, we can see for the layer of the disk, when the light incidence on the disk, the layer doesn't affect the results more because the light
I'm just saying, do you think that it will matter? Yes or no?
no.
No. Cool. That would be probably something that I wanted to discuss. And in your experiments, you only see one range. Does that mean that you've only tested one level of diffraction? One level of diffraction, like M1 to before.
It means the differential order.
Like in your experiments, I guess I'll have to ask that later. Thank you.
So it's time for the opponent to prepare. text, please.
Hello, esteemed judges and fellow debaters. My name is Yuri Gao, and I am going to give a little report. Okay. The problem statement is colored line. When a compact disc or DVD is illuminated by a light with light coming from a filament lamp in such a way that only rays with large angles of incidence are selected, a clear green line can be observed. The color varies upon slightly changing the angle of the disc. Explain and investigate this phenomenon. And they focus on results by changing the angle of the disc and the results by changing the CD into DVD. And the summary, the theory was that they change different structure of the disc so they can change the different diffraction gating, and therefore there will be different angles. And then also the incident lights will also affect the diffraction angle, and the difference of CD and normal gating will also affect. And use the derived formula to gain the wavelengths, like what they thought would happen. And the setup is they use simulation like Python to get the intensity of the light. And they use CD and DVD and also darkroom and protractor. Parameters are different diffraction materials and different angles of incidence, like I mentioned before. And analysis is the different colors on this by changing the angle and by different material. And their conclusion was that the angle and between the normal disk and incidence of light will be influenced, but I don't think they actually made a clear formula or something to explain this. And also the distance between the Jackson slits will also affect the color. And their advantages was they had a great demonstration video, and they had also clear mass derivation and also a clear setup to let us know what they did. And our suggestions was they didn't have too many variables, and also they didn't have clear conform to expectations. And yeah, since you should have derived from the formula. And these will be my points of discussion later, are the different levels of diffraction and different layer of disk. And one cool formula right here is the gating equation formula. And yes, that would probably be the end of my report. Thank you.
Looking forward to discuss with the reporter.
Can you briefly explain how diffraction works?
You mean diffraction? Okay. So as we know that the diffraction grating on the CD is like this. So when the light is an incidence on this grating, the grating on it, the light will diffract in different directions.
Okay, and so how do you define those angles?
But for here, this angle is the diffraction angle, and you can use the formula you show on your slide to discuss the angle of this. For the different angle of the spins. But for my experiment, I'm not calculating these spins traveling in different directions. For my experiment, for me is to calculate that the light source incidence on the disk, and the structure on the disk will reflect the light back to the observer and one of the light scenes. So not the diffraction grating, because the diffraction angle, because when the light incidence on the disk, the diffraction will be like this.
Okay, thank you. But one thing I'm trying to say right now is, do you agree that you failed to give a clear formula? In what angle can you see what kind of light?
You mean the color of the light on the disk?
Yes. And which angle can you look see different.
Because for my theory, I have the formula derivation. I get equation B as here shows, and can use to analyze the color of the line on this.
Yeah, what I'm saying is like, if I have a formula and I have the angles of incidence right here, and then I could guess what kind of color of light I want it to see, and then I could have and put out is the angle that I can see that color of light. You fail to do that, and what I'm trying to do right now is do that for you.
This I have to do in my theory simulation. As here, we can see when we change the different angle alpha and angle beta, we can have the different color of the line on the disk. For here, we can see when the angle alpha and the beta is 0 degrees. This is a clear green line on the disk. So we can have the color of the line clearly.
Again.
For my simulation of the theory, we can see that when we change the angle alpha and angle beta here, we can have the clear color of the line on the disk.
Angle alpha is what? Can you draw it out?
Okay. Well, for my angle alpha here means that when the light is incident on the disk, it can reflect back to the observer. So the angle alpha here means that we can, and as my theory says that the line is bisecting the point O and point S. So the angle alpha here means the reflect angles or the incidence angle of the line.
This is angle alpha, and what's beta?
Well, the angle beta means the inclined angle of the disk. So if this is the disk, and when we do the inclination, the disk will change like this is the disk, and when we incline the disk, this will be the angle beta.
Okay, and so do you have a theory line or something?
You mean a theory? I have mentioned in my formula derivation here just the angle alpha and the angle beta.
Yes, but what you told me was that how you changed the angle of incidence was you changed this, right?
Yes.
You changed this, so I think we have like a big misunderstanding. So I'm telling you that you don't have a theoretical value, or do you?
My simulation is based on my theoretical model, so I have the value of the finger use extension.
Okay. I'm going to write like I'm saying that you change this, and then you change this, right? You
Yes.
change this, and you're supposed to be able to write how many. But when you change this angle, like this is better, right?
Yes.
When you change beta, you can get one kind of light right here. You should be able to write that. And I'm trying to do that for you since you failed to do it in your project.
It means like when the light is incident on the disk, that will reflect in different directions, and the color of it will be different.
I mean, when you change this in different angles, you should have different colors.
Yes.
Yes, and I'm going to write a formula for you. Thank you.
But for the formula uses shows on the slides, and you can get the when we change the angle beta and angle alpha, we can get what will the color be.
For example,
For
I give you
example.
alpha is 30 and beta is 30. Give me a light.
You mean the angle beta is 30 degrees? 30.
Yeah, 30 and 30. Give me a color of light.
For the simulation, we can see when the angle alpha is 30 degrees and the angle beta is 30 degrees. We can see the color of the line on it will be the green line for my theoretical simulation.
Yes, but you didn't write a formula out. I'm sorry, I was the one that misunderstood. I'm sorry.
I'm going to explain about my simulation. Well, my simulation
Okay, I
is
get
based
it.
on the formula I showed on my
I
slides
get
here.
it now, I get it now. I was the one that misunderstood you, I'm sorry. And, then did you check like, okay, then let's talk about different layers of the disk. Then different layers of the disk, like, you know, there are this, right?
Yes,
And there will be another layer like that.
like plastic.
Plastic, yes. So when the light comes in, there will be a angle difference right here. Do you agree?
Yes,
Then did you calculate that in your formula?
because for here I already calculated about the layer of the disk. We can see, even though there's another layer on the disk, when the light incidents on it, the angle will be different, which means that the angle is when the light is reflected back, which means the angle only will be another different angle. So it will be like when the light is does incidence on the plane.
Well, then this will be your real like angle of incidence, right? This will be the real angle of difference incidence. So when this changes, your angle of difference should change. So when you're using that model, it wouldn't be like so accurate.
Okay,
Is that correct?
I see.
Yeah. So when I was asking short questions, you said that this would not matter, but I think it would matter, and it wouldn't matter like probably quite hard. And that might be some errors you want to put in your other formulas,
Wait, you mean which formula?
like the formula you said right now.
This formula?
The formula you can be giving me like 30, 30.
As for the 30-30, we can use this formula and calculate the color of the line. So for here, we can see when the beta is 30 and the alpha is 30, we can see that the color of line on the disk will be green, because for my simulation is based on my theoretical models and using the equation that I showed.
Yeah, but your theory is using this angle, not this angle.
For the angle here is it just has a minor change, so it doesn't.
Why? I can calculate for me that it's a minor change, not a major change. Do you know?
Because it's an incidence angle on it and the reflect, when you reflect back, and the angle on it will be the same. So
It's like you're telling me, it's like this, but I'm telling you, it's like this. So when this changes, this will change.
but when the light incidence on it, it will be like this.
Yeah.
But for the reflect light, it has the same. So you won't change the results because this angle is the same. So
But this will be, like I said before, this will be the real angle, like real angle of incidence. So when you're calculating the angle of incidence, you should be able, you should probably consider the fraction, not the fraction, this angle.
but for here, the reflect light has the same angle. So
Yeah, but that's not the one that you put in your Python thing. This is what you're putting in your Python thing. This is what you're supposed to put in your Python thing.
but for here, we can.
Can I start?
Thank you.
Aparna has 1 minute to summarize.
First, we had quite a big misunderstanding on the formula of that, but I think that in my opinion, they use this like two-dimensional polar, the graph, so it would be a little bit hard for me to understand, and probably something that they wanted to improve later. And also we reached a consensus that the different layers of the disk might affect what we want to see. And that would probably be it. Thank you.
Okay, it's time for reviewer to ask questions.
Have you considered the influence of the plastic film or the layer on the, for example, your CD disc?
I've considered it and it's no matters.
Okay, do you think the plastic layer on the CD disc will matter?
Yeah.
Okay, do you think that would change the index of refraction, as you said before?
Yes.
Okay, so the reporter talked about adjusting the angle of incident and the CD type. Do you think there are other relevant parameters that they should have tested?
Different lights versus like parallel lights or different. Let's say they gave like a light that's flashlight, so the light will be this way. But if they use like parallel lights, there may be different changes.
Okay, okay. And then, do you think that since you guys were talking about the angle of the incidence, do you think that the reporter's definition for it is rigorous enough?
Again.
Do you think the reporter's definition of the angle of incidence is rigorous or enough? Like he clarified it enough?
I believe he clarified enough. Yeah.
All right. Since you mentioned about the angle of incidence changing when there is a distance over there, do you think the index of refraction, for example, needs to be considered when correlating with the angle of incidence?
So can you say the question again? I think I didn't get your point.
Yeah. So since the opponent talked about the index of refraction, do you think it should be considered as well when you're correlating with the angle of incidence?
Yes, I should consider this.
Okay. About experiments for the opponent, at large angles of incidence, do you think that the color spectrum, as it widens, do you think that the reporter's method of identifying the green color's measurement is accurate enough?
Green color?
Yeah. For example, its intensity.
Well, it might be accurate enough, but they didn't actually define the color green or something, like the wavelength.
And for you as well. Then the opponent, the reporter included proportional. Sorry, not proportional. Okay. Do you agree that the reporter should include numerical theory correlation instead of just matching with the intensity graphs?
Yes.
All right, so the preparation time for reviewers, you have 2 minutes. So it's time for reviewer to take the floor, 4 minutes.
Hi, my name is Justin Wang, and I'll be reviewing for number 4, colored lines. Alright, so this is the problem statement. When a compact disc or DVD is illuminated with light coming from a filament lamp in such a way that only rays of large angles of incidence are selected, a clear green line can be observed. The color varies upon slightly changing the angle of the disc. Explain and investigate the phenomenon, and we believe that the color variation will depend on the angle of incidence and also about the green line's visibility depending on angle of incidence. Alright, so for the reporter, they went through the phenomenon and theory. Specifically for the phenomenon, they talked about how when the light illuminates a compact disc, a green line will be displayed. And then they talked about the scalar diffraction theory, determine lambda, and then use simulations to determine the green color intensity. And for experiments, they tested various incidence angles and used different types of CDs. And they concluded that these parameters would affect the color's intensity. However, some of the pros and cons for the reporter's performance is that even though they clarified a lot of their definitions, for example, like their disk structure, and then they also clarified the difference between a CD and then a regular diffraction grating. At the same time, they also tested a few relevant parameters. They had unclear phenomenon demonstration for the incident angle changing, and then they also had unclear explanation for how the intensity graph was actually determined from the simulation. And then at the same time, they also only have observable correlation between the theory and experimental colored intensity graph, and that because of that, they have no numerical correlation. As for the opponent, some of their pros was that they summarized the reporter's presentation well, and then included important points that the reporter talked about. But at the same time, during the discussion, he had poor time management and unclear communication about definitions. And some of the discussion topics they talked about, the opponent asked about is is the theory that they included in their slides accurate for the green color's boundary definition? And the reporter replied that they already clarified what alpha and beta is. However, even though they include alpha and beta, we believe that they still need a numerical correlation instead of just an observable relationship over there. And then the opponent further asked about the actual angle alpha and angle B and its definition on their diagram. The reporter tried to explain it to the opponent, but I think that they can do a better job about explaining alpha and beta. At the same time, the opponent asked about deriving the theory. However, I think he made a mistake. Okay, and then they also talked about how the angle of incidence will change depending on refraction on the disk surface, and we agree with the opponent because that is something that needs to be considered. However, there are also some points that they missed about. For example, they didn't mention about having negative first order or different orders, and also first order, positive first order diffractions. And at the same time, during the discussion, they pointed out the index of refraction of n when angle is changing. However, they didn't discuss enough about how the plastic CD surface would affect the index of refraction. And then some of the points missed for the report is that they still need to clarify how the green intensity graph of Python is determined.
Okay, stop. Now our reporter has 2 minutes to conclude.
Here's my concluding remark. For my report's highlight, I explained the difference between the CD and the regular diffraction grating, and use Python to do the simulate and have the qualitative analysis between the theory and my experiment. And for the discussion revisit, we think the color are more clear than the number of the wavelengths, and we had also shown the exact value of the wavelengths on the experiment result. And due to the same materials, reaction will be the same. We think the opponent's confusing wouldn't affect the result. And for the theory shows that the wavelengths below our experiment results here. And for my fixing point, I think I can do more parameters such as the different kind of the light source that the opponent have mentioned. And here's the end of my concluding remarks. Thanks for your listening.
Okay, so it's time for jury to ask questions. Any question from jury?
Okay, so I want to ask a question for the reporter. In your slides, you say you want to do the different kinds of light source. So I just wonder what kind of parameter you want to change for the light source.
Because the opponent have mentioned that for the filament light is they scatter light to the disk. And he suggesting can use the parallel light to incidence on the CD and see if the results will change.
Also means the angle, right? I saw that you're talking about the color of the light source. Because I think in the topic you said filament's the length, right?
Yes.
I thought you were talking about the color of the filament length.
No,
Because they have different colors distribution for the RGB, right? Red, green, and blue, right? I was talking about this one. Can I have one more question? Yeah. So in your experiment, you didn't come to how can you go back to the slides that you want to do the experiment? The picture, yeah, the one. So you don't put any bolt in front of the lamp, just to make some small hole.
For my experiment, the experiment setup that I use is like
Something like a slide, slit, the small slit. You didn't do this one. So this made me confused in somewhere.
And for my
You don't put any slit.
that the lamp is closer to the table, which means that only the skimming light or incidence on the disk.
But they still have some angles from the lamp. So how can, yeah, sure.
Yeah, I can add to that.
You want to do something? Yeah, okay, sure.
Yeah, they use a lamp, but however, the suggestion for me would be that you can just use a laser, which is much more narrow and with no different
Yeah,
angles.
but the target is not using laser, it's a lamp. So you cannot use a laser. Yeah.
Yeah, too similar.
Okay.
Okay, so I would like to ask the reviewer, mention something. What is the physics behind to observe the green light only?
Physics behind observation.
Yes, what's the physics mechanism?
By making sure that when you observe it, only the green light is determined by their intensity graph. And then by determining that, they can correlate with the feature for the green light.
So what is the physics model? Yes, to observe only green light.
I believe they use the Python simulation for that.
No, I just would like to know your opinion.
Oh, okay. As the index, as the light refracts from, let's say, the disk surface, it will create a color spectrum, and then it will have different locations. For example, like red, green, and then blue. And then in the middle, let's say, in the middle wavelength is green, and you can determine the green wavelength with the green position.
So maybe same question here to the opponent.
Pardon me?
Same question.
Same equation.
And the same question.
Can you ask the question again?
Yeah, what is the physics model? Yeah, to observe the green light only.
The green light only, then I believe you would have to just change, like this is the disk and this is the light source and this is the observing. And you can change this and that, and you can observe a green light, and you can put it into like image analyze apps, and then you can see the wavelengths of the green lights between a definition, then that would be called green lights.
Okay, my question to reporters, could you correlate your alpha and data to the large angle? How do you correlate that?
For my experiment, I have controlled the angle alpha as 20 degrees. And for my angle beta, I think for
Okay, my conclusion is that for example, alpha and beta here, I think it's, to me it's small, 20 degrees. But how you calculate this 20 degrees, the small number, the angle to large angle?
Yes,
From
for
the
my
statement.
for the beta here means the angle of the incident. The angle of the angle of the incidence is the 90 degrees minus the angle beta. So and the problem statement says it's the large angle of the incidence. So for this picture, we can see that the angles of the incidence is 80 degrees. So it's, I think it's the large angles.
Okay. So it's time for jury to consider the score. Ready? So now it's time is a score for reporter. That's 8, 7, 7, and 7. Okay, so now it's time for the opponent. So it's a 6, 5, 6, 6, and 7. And now the score for reviewer.
Is it right?
Okay, could you show the score again?
Again, for
For the
opponent?
opponent?
For opponent.
他们有那个 paper 上面去。6, 5, 6, 6, 7. 6, 5, 6, 6, 7. 对啊。6, 5, 6, 6, 7. And now the reviewer, for the reviewer. Okay, all 7s. Okay, so thank you everyone. And we should have 15 minutes left. And sometimes you should rotate the table. Have your seat, please. All right, so we should start the opponent has 1 minute to challenge the reporter.
The opponent would like to challenge number 8 Euler's pendulum.
Number 8. The reporter can consider for 1 minute.
We also have a challenge.
Okay, number 8 is the assessment. reporter, you can take the stage.
Hello everyone, my name is Guoping Chen and our team is Mr. May. And our topic is Euler tensor. And let's go on to the outline and then we'll discuss about the problem statement and experience video, the theory, experience method, and experience 1 dependent of magnets affects the oscillation. Experiment 2 to see if the thickness of plate affects the oscillation, and 6 conclusion. And the problem statement right here, we highlight we deflect the oscillate, it touches the plate only with the highest edge and release it. Study the motion of such a pendulum under various conditions. And our main focus is about the motion of pendulum. And here is our experiment video. As you can see, the maximum of the swing angles decrease every time, at every collision. And let's go on to the theory. And if the magnet is the uniform mass material and its inertia is equals to this, and the L is the length of the magnet below, and the R is the radius of the magnet below. And according to a research paper, the attraction force between the magnets can be derived from the total magnetostatic interaction energy of the system E, according to this. And then the attraction force can be expressed as follows. And Fm equals to this, and JD is the math calculation right here. And JD is the dipole coupling, and J1 of Q is the modified Bessel function of the first kind. And Z is the distance between the center of the two magnets, and the joint of Q equals to this. And we can now do a partial derivation in the Fn, and Fn equals to this, and by changing the JD into a sigma form, and we can get this. And due to its fast convergence, the Fm can approximate to this equation. And according to our model, torque can be written as the I alpha equals to the torque of the magnetic force and plus the torque of the gravity and plus the torque of the damping. And right here, this one is the torque of the magnetic force, and this one is the torque of the gravity, and this one is the torque of the damping. And when the L is more longer than the X, and we can approximate this one to this one, and the X equals to this. And we define the theta is the initial theta times the cosine omega t. And we can get the alpha right here and equals to the omega squared times the theta. And we got the I and we got the I times alpha before, so we can get omega squared right here. And here's our experiment method. Step 1, deflect the rod to the highest point and release it. And record the experiment with the smartphone camera. And we use Chaco to analyze the video. And our experiment set up that our equipment is the thickness of the plate, and the plate is about 2, 5, 8, 11, 14 millimeters. And the thickness of the magnet is 4 millimeters, and weight is 2.65 grams per magnet, and radius is 5 millimeters. And the purpose is to change the length of the magnet and above and below of the plate, and observe the time and the oscillation of the magnet. And this is our manipulation variables, control variables, and the result. And we take 8 centimeters as an example, and we can use this raw data to find that the maximum swing angle will decrease, and the time of the period also decrease. And the vertical of the axis that we use the period, and the horizontal use the number of the pulses. And here, we use the vertical axis, we use the maximum swing angles, and the horizontal one, we use the number of collisions. And here is our experiment data right here. And the orange one is the theoretical curve. Due to the theoretical is too long, so we just don't show that in this slide. And we can find that it does fit our experiment data. And this is 64 millimeters right here, and also it is fit our theoretical curve, and also 72 millimeters. And it does fit our experiment data. And 88 millimeters is also, and 96 is also fit our theoretical curve. And here we put the whole length on this table and on this graph, that we can see that 64 millimeters decay of the period is more than the others. And also the maximum swing angles decay 64 millimeters is also larger than the others. And here is the initial period. And the theta decay, we can find that it does have the chance that when our rod is more longer, the theta of the decay will be smaller, and the period of decay will be the smaller too. And discussion right here that when the rod is getting longer, its decay coefficient of the maximum angle getting smaller, and its decay coefficient of the period is getting smaller. And our experiment 2 is and we change the thickness of the plate, and we observe the time and the oscillation of the magnet. And this is our manipulation variables, control variables, and the result. And here's the thickness of the 2 millimeters right here, and we can find that it also, right here it also fits our theoretical curve. And we have 5 millimeters. It also fits, and 8 is the same. And 11 millimeters right here is also the same, and fits theoretical curve. And when the thickness is 14 millimeters, its decay is nearly close to 0. And the maximum of the swing angle still has apparent decay. And we can find that the data also fits our theoretical curve. And see right here, the 2 millimeters of the plate, that the decay of the period is very apparent and larger than the others, because we think that the magnetic force is more stronger than the others, than 5, 8, 11, 14 millimeters thickness. And the maximum of the swing angle is also the same. And here is our initial period right here. And the theta of the decay, we find that when the thickness is more thicker, and the theta of the decay will be smaller, and the period of the decay will be smaller too. And when rod is getting longer, its decay coefficient of the maximum angle getting smaller, and its decay coefficient of the period getting smaller. The theoretical curve fits better than the short length. It fits better when the rod is getting longer. And here's our conclusion. When we change the length of the rod, the shorter the rod is, the theta and the period will decay more. And relative to the magnetic force, the gravity affects more. And number 2, when the plate is thicker and when the plate is thicker, the theta and the period will decay less. Due to its magnetic force will affect less. And number 3, the thicker the plate is and the longer the rod is, the theoretical curve will be better and more approximate to the normal pendulum. And here's my presentation. Thank you.
Okay, so it's time for the opponent to ask the question.
Okay, so reporter, thank you for your presentation. Could you go back to your slide where you have the video?
Yeah.
Okay. You can see how the magnet slides on the surface and it's changing the axis of rotation every time. So did you account for how it changes the axis of rotation?
No, and the rotation is not apparent, and we just look at the vibration right here.
But when it changes the axis of rotation, it's gonna, like, you can't apply the rotation motion.
But we just release when the velocity is.
So I'll go to the next question. And then, did you know that B field is going to be different everywhere under the surface?
Can you say it again?
Did you know that B field generated by the top magnet is going to be different below the surface?
We just measure it, and when the magnet is more than 2, the magnetic field doesn't change it a lot. So it just.
When the decay gets smaller, how do you quantify? Did you quantify the decay, or did you just say smaller?
Yeah, we quantify it just like here. To show you that.
And did you track the motion of the end of the magnet?
The end of the magnet? No. We just check the.
Okay, so no. Did you when you did Bessel function, did you consider the B field of the magnet? Or the magnetic field?
The Bessel function doesn't have a combination with the B field.
for a second.
All right, it's time for opponent to take the stage.
Hello, my name is Judy, and then I'll pose problem number 8, Euler's pendulum. So the problem was take a thick plate of non-magnetic material and put neodymium magnet on top of it and on the bottom of it as well, and deflect the rod so that it touches the plate only with highest edge and relief. Study the motion of such a pendulum under various conditions. And we'll focus on external disturbances, oscillation, and damping. So some observation the reporter did well was it contains a 2D demonstration video, but it was sliding on the surface and video does not capture the 3D motion, which can be captured from the bottom, and magnets aren't uniform. And the theory, it contained a lot of equation of motion, however there's no qualitative theory that you explained, and the theory variables are very unclear, and you did not utilize magnetic dipole moment as well as magnetic field, and did not contain the body center of frame calculations, and did not determine the magnetic field. Some experiments overview, you had good contained experimental methods, tested a few parameters like size, length, and thickness, and you determined the decay got smaller, but you did not determine the magnetic field as well, and potential errors from release angles, it might not be consistent, and you did not account for the magnetic sliding on the surface, and there is not enough parameters tested, and you also did not quantify the results. So data analysis, you had some error bars, but they overlapped, so I guess it's very suspicious, and you can't really tell a lot of convincing data from it. And then you had correlation theoretical curve with the experimental data, but there is no quantitative correlation that I saw at the end. And then the magnet number, plate thickness, you didn't explain like why, by how much they changed at all. You discussed some proportional relationship based on the plate thickness and length of the magnet, once there was no correction or magnet slipping on the surface that I saw. So some discussion points that I'll go over is the theory part. I'll talk about some 2D motion, and I'll talk a little bit about Lagrangian, and I'll talk about moment of inertia, which he did explain, and some of the damping motion, magnetic dipole moments, and experiments. There was also causes of sliding, which I wasn't really clear what he was trying to say. And there was also changing of the distance, length, and the number of top magnets, which would have changed the magnetic field. And there was also release of the magnets in terms of angular velocity, which was not seen in the presentation. We'll also talk about fitting the data into theory more and relating this data to conclusion. So we can move on to discussion. So I mentioned that, how did you control the angle to be consistent?
The angle of the back.
Yeah.
Angle of what?
Angle of release.
We just, here is the plate, and here is the rod. And we just release it when the angle is 90 degrees, and we release it when the velocity is 0.
Okay, so that's great. So why don't we think about looking from the bottom view?
Oh yeah, we do use the bottom view and check it.
Okay, so video was not included in the presentation, so I wasn't sure, but how did you make sure that this is always 0 degrees to this line here? Because if there was some initial angle here, it's going to alter the motion because the initial condition of your experiment is going to be different.
Say the angle, you said that when the initial position is right here.
Yeah, so you might have released slightly like this way.
And you will move like this way.
Yeah.
And it doesn't have a, we just use the ruler to put it right here, and we just
Okay, but you realize that when you release with different initial angle, it's going to have a completely different motion from when you release from the here. Because assuming that the magnet is uniform, when you release completely at 0 angle, it shouldn't have like this circular motion at all. And it should go like this way, only 2-dimensionally.
But,
So, yeah.
but just like you said, the motion will be a circle, but it is when the velocity, the initial velocity is not 0, and we control it with the 0.
Okay, so I saw also your equation also had theta as an angle variable, right?
Yeah.
What I would suggest is using the Lagrangian coordinates, which is if you have x, y, and z here, and let's say this is your magnet, inverted upside down, so there's going to be your top magnet here, you can use the rotation of this magnet as a side, because you're also going to have the rotation of this magnet, right?
Yeah.
Not with respect to the left, but with respect to itself. The magnet is going to rotate like this way, okay? And then when you project it down here, you can also see that the angle of this on the xy plane is going to be phi, and then the angle here is going to be. If you use these 3 angles, psi, theta, and phi, you can model the motion in 3D.
But we just
Instead
want
of
to
using
control
only
it,
theta.
it is 2-dimension, and we don't want to discuss about the 2-dimension on
Okay.
how it's given.
But if you only assume it's 2-dimensional, it's not addressing the problem because 3D is going to have completely different frequencies, and they're going to have different time for periods as well.
But our theory is about the 2 dimensions, but our theory is our experiment data, so I think it's not a big problem right here.
Okay, I guess you didn't address that part of the problem statement. So I also saw you had something like moment of inertia being equal to that, right?
Yeah.
But this is only accounting for the moment of inertia when it's 2D as you use in the motion.
Yeah.
But since it's not in 2D and the motion is in 3D as you can see, you should use moment of inertia as a vector, which includes this as an x component, I of x, I of y, and I of z. Because when you only use this I, you're saying that moment of inertia of a rod, for example, it doesn't account for like the 3D motion this way. But if you use x, y, and z components, you're going to have the moment of inertia expressed in the whole system. Yeah.
But we just on the 2 dimensions, so yeah, just don't talk about the 3 dimension like it's not.
Yeah. Also, you notice how when you say there's a damping that slows it down, and then essentially it comes to a stop at the end, right?
Yeah.
So how would you explain that, like these friction or like damping? How would you quantify that? Because I couldn't see it in your presentation.
We think the damping is not the main reason that because I think the magnetic force is more affects more than the damping, and the gravity also affects more than damping a lot. So yes, it's just our theory.
Well, didn't you say your torque is going to be the torque of the mechanical or magnetic, and torque of gravitational, and torque of damping?
So we just ignore the torque of the damping right here because we think it's not the main focus on it.
Okay, but you realize that if you just assume this is not present, the oscillations keep going to go and it's not going to stop at the end, right?
But the decay is caused by the magnetic force right here, and if your plate is more thickness, the magnetic force will be smaller, and so you will consider to be a normal. You approximate to a normal pendulum right here, so it just affects relative to the we just take it for example 10 millimeters and 2 millimeters right here. And relative to this, and we can see it as a normal pendulum right here.
Okay.
Its decay is not affected.
That's great. So I saw also your force, which was very complicated. Is there a reason for that? Because I think you can start from the formula that we all know, and we simplify it this way, right?
Well, we don't use the ampere right here. So we just use
Because I think the B field is actually what dictates in this problem, because the problem statement says like the top magnet has to impact the motion of the bottom magnet. So if you explore the parameters of changing the top magnet, this B is going to change and your entire force is going to change.
But I think the force is used in the line and it could
Okay, so can I just give you a suggestion for that? So I would say when you start from I times, and then you divide it into the B of Y, you can rearrange these terms, and then you can have IA, which is the dx times dy component, and then you can also have the by. You can simplify this into force being equal to the, if you take the gradient of the magnetic dipole moment and the B field, but I didn't see both of these considered in the presentation, which dipole moment is considering how much of the motion the bottom magnet has. Then the B field is the field generated by the top magnet. So there's going to be a B field in the region here that's going to have it. So you see how like the field here, this point is going to be different from the field here.
We just turn the magnetic dipole moment into the magnetization. So I don't use the magnetic dipole moment like this.
But do you acknowledge that it's going to change as a function of time? Because at different position, it's going to be different.
And the magnetization is if your volume is
So could you explain with your slide your equation? Because I didn't see how it's going to change as a function of position. The complicated one. Yeah. So how would you define that the field or the dipole moment is going to change based on your location of the magnet? And how did you how did you solve the model?
And here we just calculating right here. So we just change the JD into the thing that we write before, just like this. Just like this. The J1 of Q, we just change it into the JD, and we can take the JD off and use this equation right here.
Okay. So and then you also saw that how I mentioned about psi. It's going to be the rotation of the magnet along its axis, right? So when it has a pendulum motion, it's also going to rotate like this, the magnet itself. Did you track this one as well?
No, but we're just gonna check the motion of the maximum free time right here. So
Okay.
it's not all.
But this is also going to change it. So I think if you use the Lagrangian coordinates, which accounts for also the rotation of the magnet by itself, you can use way simpler formula, in fact, to solve for the force, which can be also including the psi formula.
Yeah, it's good, but it's not in our like.
And you also had mentions about collisions. Could you go back to the slides of collisions and define collisions? Because what collisions are you talking about in this problem statement?
Collision right here, when the rod goes to the left, and you will be like this one, and this one, this angle will be this. Let's say.
Okay, but you realize that you define this as an axis of rotation. Well, when this switches to this point is going to be axis of rotation. So there's a distance that's going to move, which is not going to make it a circular motion.
But in the experiment video that we didn't see that it's going to be slide.
Okay. Also, could you go back to slide 47? You can see the error bars are clearly overlapping, so that doesn't really convince our.
Okay, time's up. Okay. So following the 1 minute to summarize what this project.
So in our discussion, we talked about how 3D motion is very essential to problem statement. However, I couldn't really see that reporter really address the 3D motion, and was just too deep, and then the angle of release. Initial angle was also could be different because it was very not particular. And then we suggest the use of Lagrangian and moment of inertia using vectors to account for the 3D motion, instead of thinking of it as a 2D motion. And there's also friction damping on tip of bottom magnet that has to be considered, but they just kind of made it unclear of how they took an account of the friction. So we couldn't really see today. Yeah. So the second summary is you can use the formula that I wrote on the board so that you can define the new I and B, and then you can derive a much simpler formula for the force, which also accounts for dipole moments and the B field. And rotation of the magnet is not accounted for, which also can be defined by the new coordinates. And the collision, the axis of rotation changes all the time.
Alright, so on time for the review of the expression.
Yeah, well, thanks for the reporter and opponent. So we're gonna start from the problem statement. So the problem statement mentioned that we have to use a non-magnetic plate. So what is the purpose of this plate?
It is an object is made of the
What is
plastic.
the purpose?
Plastic.
Okay. What is the purpose?
You just
Oh, if it's magnetic, it's going to alter the magnetic field, so it doesn't account for the motion of those two.
Okay, I got your
it will
point.
not affect, and it will not affected by the magnet or the magnet field.
Okay, I got it. So the second question, let's move on to the theory part. So do you think you have to take the rotation into consideration?
No, because our experiment used our initial omega right here is 0, so we just don't.
Okay, I got it. And how about opponent?
Yeah, it has to be together.
Okay, so due to the opponent thing, you have to take the rotation into consideration. So do you think you have to do some future work about the rotation part?
I think we should consider about the rotation right here and the motion of it.
Okay, I got it. So if the reporter used didn't find the rotation mode, so if it's really necessary to use the 3D model.
Yes.
Okay. And the third question is about still about theory. So please turn to page 14. So first, let me ask about, do you agree with the opponent that you have to calculate the B field?
Yes.
Okay, so because different point will have the different B field, right? So it is really complicated. So how to measure the different point, you think?
I would measure the B field at different points, and then measure the B field as a function of position.
So is this equation appropriate to every situation? Do you think? Every situation.
No, because we just don't.
How about the opponent think? Is it appropriate?
Well, we talked about how using single variable for angle is not enough.
However, the reviewer thinks when x is equal to 0, it is not going to be not going to use in this experiment. So let's move on to the experiment part. So do you calculate the boundary of lengths that can appear such a pendulum? Yes. The length. So do you think the reporter have to calculate the boundary of the length?
Yeah, using friction.
Okay. So since you mentioned the decay of the movement, so the collision, the friction, and the magnetic field, which one do you think is the main reason to cause the decay?
I would say friction.
And how about the reporter?
Probably friction, right?
Okay, thank you for the reporter and the phone.
Good job.
review of this session, and I'm going to review question number 8, Euler pendulum. So here's the problem statement. And we may focus on study the motion of such a pendulum under various conditions, and the test fulfilled of the reporter is partly fulfilled. And here's the summary of the reporter's presentation. So he may focus on the motion of the pendulum, and the theory part he used the dipole calculate and provide magnetic force formula. And for the setup and analysis part, he used several magnet and the non-magnetic plate. And for the parameter part, he tried different lengths of the magnet and thickness of the plate. For the conclusion part, when the rod increased, the decay of the period would decrease. And when the thickness to the plate increased, the decay would less happen. So here's the pros and cons of the reporter. First, the pros is that he calculated the momentum inertia of the for calculation, and he also did many different parameters that I mentioned in the summarize of the reporter's presentation. And he also found the relationship of the different period and different parameters. However, the cons is that his lack of the explanation of the experimental result and unclear physics picture, and didn't analyze the 3D motion that opponent mentioned in his on the blackboard and also in his presentation, and didn't analyze the resource of the decay of the periodic. And here's the pros and cons of the opponent. The opponent has pointed out many problems that reporter missed, and the reviewer also agreed with the opponent's points and built 3-axis coordination to explain the 3D motion on the blackboard. I think it's pretty clear. And however, the cons is that he talked a lot about their own theory and didn't focus on the reporter's report. I think the opponent should more focus on the reporter's report and talk about something in his report. And here's the discussion point. First, the opponent asked about, do you consider the changing of the rotation? And the reporter thinks, we assume the axis doesn't change. And the reviewer thinks the axis of the rotation changes over time, so the movement inertia should be receded. And here's the next discussion point. The opponent asked about, do you know the B field will change in different positions? And the reporter said it doesn't affect well. However, the reviewer thinks since the reporter only considered the magnetic force between the magnet at different sides of the plate, the reviewer thinks the bottom of the pendulum should also consider the effect of the magnetic force. And here's another discussion point. The opponent asked about how do you control the release angle at the same angle. And this is also the question the reviewer would like to ask. And the reporter answered that only release at the 90 degrees. And the reviewer thinks only release in 90 degrees is a way to control the motion. But the reviewer thinks since the magnetic field isn't uniform, so the exact location should be controlled. And the opponent also asked about the 3D dimension, the motion on the blackboard, and the reporter answered they only consider the 2D motion. And the reviewer thinks since the video of the reporter provides things like 3D motion, so the reporter could analyze the 3D motion by analyzing the front view of the video. So here's some missed points the reviewer would like to mention. The first one is that the reporter didn't analyze the 3D motion the video shown, and also the opponent spent a lot of time the abbreviation, the background of the system, which the reporter didn't mention in their report. And the third point is that the opponent misused the equation of uniform magnetic field formula to solve the equation of motion. And on the blackboard, I think the B should be uniform. However, the opponent mentioned that B will change in different positions. So I don't think a uniform B can be calculated by the formula. So thank you for listening, and thank you to our reporter and opponent.
All right. So it's time for reporter to conclude. You have 30 minutes.
First of all, we do the quantitative formulas in our experiment, and we actually fit it with our experimental data well as we mentioned. We use the exponential decay, and we clarified confusions about the setup and about the releasing status. And we did consider various conditions addressed in the problem statement, but just because we didn't give the pendulum an initial velocity or the angular velocity, so we analyzed it two-dimensionally, and we appreciate the opponent's suggestion. Also, in response to the reviewer, we misheard the question, and we think that magnetic force is actually the most important factor of the decay. And our experiments didn't show the sliding, so this is why we didn't consider the friction crucial factor. And this is my presentation. Thank you for listening.
All right. It's time for jury to ask questions. Any? So let me ask the question first. So to the reporters, at the beginning you showed that the relation between the force and the gradient of energy. Then, but in the analysis, I just want to make sure. In your analysis, do you use this formula?
Yes.
So you you calculate the energy and take the gradient.
We just calculate about the torque, and we get a force at first, and we got to calculate the torque right here.
Right. So to the
Because we think the energy decrease is nearly
because in your analysis, I just see the equation of motion. I did not see the potential energy or kinetic energy. So that's why I just want to make sure. Okay. So for the opponent, so you consider you think it's necessary to consider the sliding of the axis,
Yes.
and will not be taken into account into the Lagrangian. This effect cannot be taken into account to the Lagrangian method. Any other questions?
Yeah. And for the opponent, for the report, sorry. In your experiment, you put how many magnets put on the top of the sheet?
just the same as the below one. The
Same as below one?
Yes.
What's the reason you want to put the same?
Because our theory is used the same magnets on below and above and below. So we just use it to set up the experiment.
So it means if you change the number of the magnets, you will not see any difference, right?
What?
If you change the magnet numbers on the top, you will not see any difference in the motions.
The motion is just about the rod below the text, and the upper one, I think, doesn't have any impact on it.
Other questions?
Okay, so let's ask the viewer and opponent. Yeah, same question. So maybe you first, okay? So which phenomena cause the decay most?
Oh, so I would say friction definitely, and also the magnetic field contributes to decay.
Okay, check. Right?
Yeah.
Okay.
Yeah, the reviewer thinks the main reason cause of decay is the friction and the collision. I think that, yes.
Another? Okay, since there's no any further questions, so it's time for jury. So it's time for the reporters. From my side, 6, 6, 6, 6, and 7. All right, it's time for the opponent. Uh, 8, 8, 7, 9, 8. And finally, for the reviewer, 7, 8, 8, 8, and 8. Okay, thank you all. We finished this stage, and we should have lunch.